All right, guys, so we're back and learning about machines and kind of the idea of simple machines and what they do. So simple machines allow people to do the same amount of work with less force. So we've talked about the concepts of work and energy, and now we're getting into why machines help you do those jobs or to perform work. So you're doing the same amount of work but applying less force. But the drawback is you have to apply that smaller force at a greater distance. So there's a trade-off. If you're going to apply less force, you have to apply it over a greater distance. We've talked about situations where objects slowed down or speeding up, and those kind of concepts are simple. So let's talk about the probably simplest of the simple machines that we're going to examine, which is just a ramp. So I'm sure you guys have all looked at ramps or inclined planes before and used them. So let's imagine we have two scenarios where in situation one, we're going to try to lift a box directly upward, and that box is really heavy, so you might not be able to lift it put it on the counter where you need it to go. In the second case, you have constructed a ramp that you're going to be able to push the box up the ramp, and that might make it easier for you, so you'd have to apply less force. Okay, so just to kind of go through the ideas of machines and how they're efficient. So to be clear, if a machine is 100% efficient, there isn't any friction in it, right? And if there isn't any friction, that means that the amount of work done by the machine is equal to the amount of work done in that normal case. So in this situation where we're lifting a box upward, the lifting the box upward requires more force over a smaller distance, and you can see that in the diagram here. So if you look over here at this side of the ramp on the left side, I drew a diagram where there's a box, we're lifting it up to the top of the ramp. So you can see this distance, which is traced in this blue dotted line, is smaller than the red dotted line, but it requires a larger force because I have to put all the force into moving it upward, right? Where with the ramp is going to effectively help me lift the box from this lower point to the higher point, same higher point, and finish at the same position, but it's over a greater distance. So the dotted red line, by accident, the dotted red line is greater, but this force that I have to apply is a smaller force. So because these two situations require or have the same amount of work performed, we can set them equal to each other. So the lifting situation in terms of the work done is equal to the work done by the ramp. And the way you can justify this is just through conservation of energy, right? So if we look at the conservation of energy of the box when it's on the floor here or on the floor here, it's the same box, so they have the same mass. Gravity is affecting them the same way, so they have the same acceleration to gravity, and they are at the same height, which would be 0 above the ground. Then you're going to lift this box up and move it from the ground up to the top of the ramp, and so they're both gaining the same amount of height, so they are both gaining the same amount of gravitational potential energy. So the change in energy done in both those situations is going to be the same. It's just one is requiring a shorter distance and one is requiring a longer distance, and the shorter distance one requires a greater force and the longer distance one requires less force. So instead of using lift and ramp, I just used kind of more generic terms like out and in. So the output is going to be this change in energy with the lifting part. So that's what we're going to get out of this work. So by pushing the box up the ramp, we are really lifting it up that distance. So the input is what the person would do while they're pushing it up the ramp, so that's why I call it in, and the output would be what the person gets out of it, which is taking the box from the ground level and moving it up to the top of the ramp. So, and since work is just F times D, which we examined in previous lessons, the force out times the distance out, that'll get you the work out. That's equal to the force in times the distance in, which would be equal to the work in. Excuse me. So we're going to set up a ratio, and that ratio is going to be for an equation that tells us what's called mechanical advantage. So the mechanical advantage basically compares the force that you can lift or force that you get output compared to the force that you have to put in, or it's the distance you put in divided by the distance you put out. So basically all I did was, if I use the little pen here, I just solved these for force on one side and distance on the other. So if I divide by force on both sides, force in, they cancel out there. And if I divide by distance out, handwriting, those cancel out over here, and you get this ratio. All right, so it's just a relationship to ratio. We call that ratio mechanical advantage. So in an ideal situation, you have a mechanical advantage that's greater than 1 because you want to make the job less difficult. So that's what mechanical advantage is talking about. Okay. So I think it's best to kind of go through a problem because that'll help us understand and apply that equation a little bit more. So we're going to basically take the same scenario. We're taking a box and we're going to move it up a ramp to some height above the ground. In this diagram, it tells us the same information that's over here. So a frictionless, so that's important. So it's frictionless, 5 meter long incline plane. So this is the distance that we're going to put in. That's the distance we're going to move it in. It's used to move a 500 Newton crate. So that's the force of the crate, and that would be the output force. So we're not pushing with 500 newtons up the ramp. We don't have to. That would be if I lifted this box. That lifting force would be the output force that we get. And it's going to lift it up to a height of 1 meter. So this distance out is 1 meter. So we got distance in, distance out, and our force out. Part A wants to know the mechanical advantage. So if we go back to our equations, mechanical advantage, we use whichever one makes sense. We know the distances, so I'm going to use this one. So it's distance in over distance out. So the distance that I'm going to put in is 5 meters. The distance out, I'm going to get 1 meter up. So 5 divided by 1 is just 5. So 5 is the mechanical advantage of this situation. From that, we can also figure out how much force we would have to apply to make this box move this 5 meters. So the advantage part is that our force in is going to be smaller than our force out. I don't have to lift as hard comparatively pushing it up a ramp compared to lifting it directly up. So we can go back to this mechanical advantage equation, but this time we're going to use our force out divided by force in. So that's just like this part of the equation. So again, we already got 5 as our mechanical advantage. The force out, we're going to get 500 newtons moving up. And what we have to put in is what we're solving for. So I'm going to cross multiply. So it'd be 5 times force in equals 500. And then I'm going to divide by 5. And we get 100 newtons is what I would have to push with to move that box up that incline. So moving along, that's just kind of using that mechanical advantage idea. We're going to get into efficiency in a minute, but it's kind of efficiency is based on kind of how effective you are at getting things done. So efficiency is usually a percentage. So if you're 80% efficient or 50% efficient, so it's like how well you do, right? So for us, for these types of situations with machines, we're going to measure the work out, the output divided by the input. So it's like how much effort or work do you put in compared to how much effort or work do you get out. So if whatever you put in is equal to what you get out, that's 100% efficient, which is the idealized situation which nobody can ever attain. So efficiency is really always less than 100, but we have idealized situations to make problems simpler. So if it's a frictionless situation, that's how we can use all those equations because it's 100% efficient. But if there was friction, so that's question C, if there was friction, how would that force change? And I actually left this up there from a previous lesson. So if there's friction, you'd have to push harder, right? Like it would be more difficult. Friction acts against you. So you're gonna have to put more effort in. You're gonna have to apply a bigger amount of force. You're gonna have to do more work because some of that energy that you're using is not being transferred into the box or the crate. It's actually being changed into heat and sound or those non-efficient types of energy. So in part D, it asks if the incline plane was only 75% efficient, how much force would you have to apply? So just kind of going through percentages again, 75%, that's like 0.75. So whenever you see the percent, that just means divide by 100. So if we do that, you get 0.75. So that's the value we're going to have for the efficiency. So the efficiency is 0.75. What we need to do is how much force would you have to apply? So I'm going to start with work, and then I'm going to kind of solve for force after I get the work, right? So again, efficiency is the work out divided by the work in. So I think we can do this pretty well. And then once you get the work in, you can solve for either a force or a distance from the work equation where W equals FD. So if we think about this, we have a 0.75 efficient ramp. The work output is what we're going to get over here. So we get out 500. And we want to figure out what we have to put in, right? So if you ever get a number here, like I would expect the work in is bigger than the work out because like I'm not going to be able to be as efficient, right? So I'm going to, again, cross multiply and solve. So I have 500 equals 0.75 work in. I divide by 0.75, just showing you the math along the way. So 500 divided by 0.75 is something like 666.6. So I have my work in is 666.6 joules efficient, and I'm going to use this ramp still, right? So in work equals F times D. So the distance in, and this is my work in, right? So my work in is 666.6. My force in is what I'm solving for. And then the distance in would be how far I'm moving the box up the ramp. So that's still 5. That hasn't changed. So this is just going to be 5. So that's still 5. So I'm going to divide this number by 5 on both sides, and I'll get the force that I actually have to put in. So the force that I have to put in, if I take 666.6 divided by 5, I get something like 133.3 newtons. So as you can see, ideally, we said that we only had to put in 100 newtons of force if it was an idealized frictionless situation. When there's friction, we have to push more. So again, it's kind of like, I would say the steps, we use the mechanical advantage equation with the force out over the force in, or the distance in divided by the distance out. That's either one of those is mechanical advantage. It just depends on what you're starting with. Then we kind of used our efficiency equation, which is just the work out compared to what work you put in. And then we used our work equals FD equation to get to whatever variable here is missing. Usually it's going to ask like how much you actually have to push if it's only this efficient. Okay. So there's one more here. I'm going to let you guys try to figure this one out a little bit on your own. So I'll pause the video at different points, but we can read through and talk through it and go through. So in this one, it says a ramp is 15 meters long, has an ideal mechanical advantage of 20 meters, or 20, excuse me, I said meter, but ideal means frictionless again. So there's no friction in the first part of this problem. Okay. So first question is, we said the ramp's 15 meters long. What is that going to be? So meters is a distance. Is it the in distance or the out distance? So is it the distance you're going to move the box, or the output, which is the outcome of the thing? So let me ask you that question here. And this would be the in distance. So 15 meters is how much you're going to put in. Mechanical advantage, that's MA. Mechanical advantage, MA. And that's 20. All right. The height of the ramp, that's over here. That's the distance out. So we're trying to figure out how much we get out. So for part A, this isn't too bad. It's just the mechanical advantage is the distance in, or I'm sorry, distance out. Make sure I say this right. Yeah. Distance in divided by distance out. Okay. So the distance in is, distance in over distance out. Yes. So for mechanical advantage, we said that was 20. That's a value of 20. 15 here, distance out. We're actually solving for how far is the height of the ramp? How far are we getting? What are we going to get out of this motion? So again, solving the distance out would end up being 15 over 20, which is 0.75 meters. It's meters because it's the same units that you have here because it's a ratio. So 0.75 meters is the distance. So it only raises it up 0.75 meters. So it's not a very tall ramp, but it's pretty long. So for part B, it says if the person applies 200 newtons of force to the object being pushed up the ramp, what is the maximum weight of an object that we can lift? So this is our force in here, and we're looking for our force out. So again, going back to our equation here, it's going to be out over in for forces. Again, I always give you the equation sheets, so you don't have to worry about memorizing this. But for part B, we know our mechanical advantage is the output over the input for force. So for this one, our mechanical advantage is still 20. That hasn't changed. Our output force is what we're looking for. Our input force is 200. So we're going to solve for the output by multiplying by 200 on both sides. So you get your output force to be something like 4,000. I wrote in 4,000. So so we can lift a 4,000 Newton object by applying 200 newtons. So again, that's the advantage idea. Like it makes it easier. We apply less force just over a bigger distance. Okay. The last part here is part C. And part C is if there was friction, and the maximum weight of the object is only 2,800 newtons, what is the actual efficiency of the ramp? Okay. So so we're going to look for the efficiency this time. That's what we're solving for. And what we have to do for find efficiency is again compare the output work to the input work. All right. So our output work would be the force that is out, so it's 2,800 times that 0.75. So like it's going to go 0.75 up. That's what we determined. That's the height of the ramp. That's our answer to A. And now it's only 2,800 instead of our idealized 4,000. For the input, we're still putting in the 200 newtons over that 15 meters. So we can put that in our calculator. So 2,800 times 0.75 is 2,100. And if we do 200 times 15 like we did before, we get 3,000. So if we do 2,100 divided by 3,000, that gives us 0.7 for our value, which means that it's 70% efficient. So it does 70% of the work that we put in, we get out. Okay. So hopefully these problems help clarify this concept. It's not something I'm going to stress a ton, but it is something that you will get assessed on. So make sure that you can understand these formulas and do similar problems to this. So I'll let you go there. Have a great one, guys. I'll talk to you later.